Q learning in deep Q networks, DQN. Today, we are going to explore two of the most important ideas in reinforcement learning, Q learning and deep Q networks, also known as DQN. These algorithms are foundational in artificial intelligence because they teach machines how to learn from experience, make better decisions over time, and adapt to changing environments. To understand why they matter, imagine a game where an agent must choose actions step by step. It does not know in advance which move is best. Instead, it tries different actions, observes the results, and gradually improves its strategy. That is the basic idea behind reinforcement learning, and Q learning is one of its most classic methods. Let us begin with Q learning. Q learning is a model-free reinforcement learning algorithm. That means the agent does not need a perfect model of the environment before it starts learning. It does not need to know every rule, every outcome, or every future consequence in advance. Instead, it learns by interacting with the environment, receiving rewards, and updating its understanding of which actions are useful. The Q in Q learning stands for quality. More specifically, it refers to the quality of taking a certain action in a certain state. In simple terms, Q learning asks, if I am in this situation, how good is it to take this action? The answer is stored as a Q value. Over time, the agent learns to estimate these Q values more accurately. Think of a robot navigating a maze. At first, it may move randomly, sometimes going in the right direction and sometimes hitting a wall or trap. But after many attempts, it starts to learn which moves lead closer to the goal and which ones lead to failure. The robot updates its knowledge after every step. Eventually, it builds a policy, which is simply a strategy for choosing the best action in each situation. One of the biggest strengths of Q learning is that it works very well in small and simple environments. Because the number of states and actions is manageable, the agent can store Q values in a table and update them as it learns. This makes Q learning easy to understand and very useful for beginners in reinforcement learning. But there is a limitation. In real-world problems, the number of states can become enormous. Think of video games, self-driving cars, or robotic control systems. In these cases, there are too many possible situations to store in a table. That is where deep Q networks come in. DQN is an extension of Q learning that uses deep learning to solve the problem of large state spaces. Instead of using a table, DQN uses a neural network to estimate the Q values. This neural network takes the current state as input and predicts how good each action might be. This is a huge improvement because neural networks can generalize. That means if the agent encounters a state it has never seen before, the network can still make a reasonable prediction based on patterns it has learned from similar states. In other words, DQN allows reinforcement learning to scale to complex and high-dimensional environments. One famous success of DQN was in playing Atari games. Researchers showed that a DQN agent could learn directly from raw pixel data, without any handcrafted features. The agent watched the game screen, learned from rewards, and improved its performance over time. In many cases, it reached superhuman performance. This was a major breakthrough in artificial intelligence. DQN works with a few important techniques that make learning more stable. The first is experience replay. In reinforcement learning, the data is collected sequentially, and consecutive experiences are often highly correlated. That can make training unstable. To solve this, DQN stores past experiences in a replay buffer and randomly samples from them during training. This helps break correlation and makes learning more efficient. The second key technique is the target network. Neural networks can change rapidly during training, which sometimes causes the learning process to become unstable. DQN solves this by using a separate network to compute target values. This target network is updated more slowly, which provides a more stable learning target for the main network. Together, these innovations make DQN much more reliable than basic Q learning for large and complex problems. Now let us look at how the learning process works in both methods. The agent starts by exploring the environment. It tries different actions and receives rewards or penalties. If it performs a good action, it gets a higher reward. If it makes a bad move, it receives a lower reward or even a negative reward. Over many episodes, the agent updates its Q values or neural network weights so that actions leading to better long-term outcomes become more likely. This process is called trial and error learning. It is one of the most natural forms of learning because it resembles how humans and animals learn many behaviors in real life. We try something, see the result, and then adjust our behavior. However, Q learning and DQN are not without challenges. One major challenge is the exploration versus exploitation trade-off. Exploration means trying new actions to discover better rewards. Exploitation means using the actions that already seem to work best. The agent must balance both. Too much exploration slows down learning. Too much exploitation can trap the agent in a suboptimal strategy. Another challenge is sparse rewards. In many environments, the agent only receives a reward at the end of a long sequence of actions. This makes it hard to understand which earlier actions were actually helpful. Learning becomes slower and more difficult. DQN also faces stability issues during training. Because the neural network is learning from its own predictions, small errors can sometimes grow larger if not controlled properly. That is why experience replay and target networks are so important. There is also the problem of overestimation. Sometimes the algorithm thinks an action is better than it really is. This can lead to poor decisions. To solve this, researchers developed improvements such as double DQN, which reduces overestimation by separating action selection and action evaluation. Over time, more advanced versions of DQN were created. Dueling DQN separates the value of being in a state from the advantage of each action. Prioritized experience replay gives more importance to important experiences during training. Multi-step learning looks ahead several steps instead of just one, which helps in environments with delayed rewards. These improvements make DQN powerful enough to handle much more complicated tasks, including robotics, finance, traffic control, and strategic game playing. In real life, Q learning and DQN are used in many exciting areas. In robotics, they help machines learn navigation and object manipulation. In gaming, they enable agents to learn strategies in complex environments. In autonomous vehicles, they support learning in simulated driving systems. In recommendation systems, they can help optimize decisions based on user feedback. In industrial control systems, they can improve efficiency by learning from operational data. The reason these algorithms matter so much is that they represent a major shift in artificial intelligence. Instead of writing explicit rules for every situation, we allow the machine to learn from experience. That makes the system more adaptive, more flexible, and more capable of handling uncertainty. If we think about the bigger picture, Q-learning laid the foundation for value-based reinforcement learning. DQN took that foundation and extended it using deep neural networks so that the same idea could work in large, complex, high-dimensional environments. For someone beginning in reinforcement learning, Q-learning is one of the best places to start. It teaches the core idea of learning action values. Once that is understood, DQN becomes much easier to grasp because it is really just Q-learning with a neural network acting as the function approximator. To implement these methods well, a few practical tips are important. Start simple with small environments before moving to deep learning models. Design the reward function carefully, because poor rewards can lead to unwanted behavior. Use gradual exploration, especially in early training. Monitor learning progress closely so you can catch instability or poor performance early. And always remember that hyperparameter tuning matters a lot. In the end, Q-learning and DQN are more than just algorithms. They are examples of how machines can learn through experience, improve over time, and make intelligent decisions in uncertain environments. Q-learning gives us the core idea, and DQN shows us how powerful that idea becomes when combined with deep learning. As reinforcement learning continues to evolve, these methods remain central to modern AI research and practice. From games to robots to intelligent decision systems, they continue to open the door to machines that do not just follow instructions, but learn how to think in terms of reward, consequence, and strategy.